Hi, Tom the Professor here. It's time for another problem. Let's get started. The problem for this episode comes from the magnetism chapter. I'll put the text up on the screen if you want to play along. And as always, we will start with, what do we know? The wire that we're looking at has a length of 40 centimeters, carries a current of 6 amps, and has a weight of 0.35 newtons. We're also told that the field, the force from the magnetic field will balance the force due to gravity. Now, if we take a look here, the weight is obviously going to be pulling straight down, so that means the magnetic force has to be pushing straight up. What do we need to find? Well, we want to find the size of the magnetic field. Now, I've drawn it in here in the picture, and I'll show you how I decided what direction that magnetic field was, because that's really the trickiest part of this problem. They don't actually ask for what direction the magnetic field is in this problem, but that's where students seem to have the most trouble. So let's go through that real fast. How did I determine what direction that magnetic field was in? What I did was I used the right-hand rule. Now, when dealing with currents and wires, there's actually two right-hand rules. I don't remember if this is the first or the second, but we're dealing with a magnetic field outside of the wire, not the magnetic field created by the wire. So when we use the right-hand rule in this case, we start out, I'm going to arbitrarily pick a direction for the current, just to be from left to right. Okay, it's completely arbitrary. I can switch that up and go right to left, and I'll show you what happens to the magnetic field when we do that. So for now, the current's going from left to right. I know the magnetic force has to be upward from my previous picture, so I start with my fingers on my right hand. Make sure you're using your right hand, not your left hand, your right hand. Fingers go in the direction of the current. Your thumb will then point in the direction of the force. And then to find the direction of the magnetic field, it will be out of the palm of your hand. Or the other thing is you could curl your fingers in and they will point in the direction of the magnetic field. A lot of the time, just saying from the palm of your hand, most people will be able to see that. So in this picture here, I've got the current going to the right, the magnetic force up. So that means that the magnetic field has to be going into the screen, which is why I use little X's to denote that. Right? If I switch and make the current go from right to left instead, just reverse that, I still want the magnetic force to be upward. So I stick my fingers in the direction of the current, my thumb is in the direction of the magnetic force, and now the palm of my hand is facing out of the screen. So I've drawn little dots to denote that's the direction of the magnetic field. Okay. The rest of this problem is really pretty straightforward, so let's take a look at that. In our possible solution, the magnetic force depends on basically four things: the current, the length of the wire, the size of the magnetic field, and the direction between the magnetic field and the current, or the length. Now, the reason we need the sign of the angle in there is because we get the largest force when the magnetic field is perpendicular to the direction of the current or the length. So we'll set up, in this case, we've already set it up so that that angle is already perpendicular. So when we take the sine of that angle, we're automatically going to get a 1 for that portion of the equation. So that will leave us with the force being the current times the length of wire times the size of the magnetic field, which is what we want to know, the size of the field. So we'll solve for that field. That will be the magnetic force divided by the current times the length. Okay. We don't strictly know what the magnetic force is, but we do know that that force balances the gravitational force. So in the background, we're using Newton's first law here as an equilibrium condition to say that the force that we're going to put on top of the equation is the same as the weight. So we stick those numbers in there: the 0.35 newtons for the force, the 6 amps for the current, and the 0.4 meters, not centimeters, meters, to get an answer of 0.15 Tesla. And that's really all there is to this particular problem. And that brings us to the end of another episode. If you liked it, make sure you like and subscribe. Hit me up on the social medias. Stop by, check out the blog, and pick up some merchandise. Everything you do helps support the channel and the blog. See you next time.